Welcome to our journey into the fascinating world of the human eye and the colorful universe it reveals. The human eye is a marvel of biological engineering, allowing us to perceive the world in all its vibrant hues and intricate details. In this chapter, we'll explore how the eye works, the science behind vision, and the phenomena that make our world so visually rich. From understanding how light enters the eye to the way our brain interprets images, each step is crucial in forming the beautiful tapestry of sight. Let's begin by uncovering the basic structure and function of the human eye. Human eye works much like a camera. Light enters through the cornea, passes through the pupil, and is focused by the lens onto the retina at the back of the eye. The retina contains special cells that convert light into electrical signals. These signals are then sent to the brain via the optic nerve, where they are interpreted as images. This seamless process allows us to see objects clearly, distinguish colors, and perceive depth. Coordination between the eye's components is essential for sharp and accurate vision. Despite its remarkable design, the human eye can experience defects that affect vision. Common issues include myopia, nearsightedness, hypermetropia, farsightedness, and astigmatism. These conditions occur when the eye's shape prevents light from focusing correctly on the retina. Symptoms may include blurry vision, headaches, or difficulty seeing at certain distances. Fortunately, most vision defects can be corrected with glasses, contact lenses, or surgical procedures, restoring clear sight and improving quality of life. Prism is a transparent object with flat, polished surfaces that refract light. When a beam of light passes through a prism, it bends due to the change in speed as it moves from one medium to another. This bending of light is called refraction. Prisms are not only used in laboratories, but also play a role in optical instruments and even in nature, helping us understand how light behaves and how colors are separated. Dispersion occurs when white light passes through a prism and splits into its constituent colors, forming a spectrum. This happens because different colors of light bend by different amounts as they pass through the prism. Violet bends the most, while red bends the least. This phenomenon explains why we see rainbows and is fundamental to understanding the colorful world around us. Atmospheric refraction is the bending of light as it passes through layers of the Earth's atmosphere with varying densities. This effect causes stars to appear twinkling and sometimes shifts their apparent position in the sky. It also explains phenomena like the apparent flattening of the sun, sunrise, and sunset. Atmospheric refraction is a key reason why our view of the night sky is so dynamic and ever-changing. Tyndall effect is the scattering of light by particles in a colloid or in very fine suspensions. It can be observed when sunlight passes through mist or smoke, making the path of the beam visible. This effect is responsible for the blue color of the sky and the reddish appearance of the sun, sunrise, and sunset. The Tyndall effect is a beautiful demonstration of how tiny particles can influence the colors we see in our environment. Rainbows are one of nature's most stunning displays of color. They form when sunlight passes through raindrops in the atmosphere, which act as tiny prisms. The light is refracted, dispersed into its spectrum, and reflected inside the droplet before emerging to form a circular arc of colors. Each color bends at a slightly different angle, creating the vibrant bands we see. Rainbows remind us of the beauty and complexity of light. Cornea and lens are crucial parts of the eye's optical system. The cornea is the transparent, curved front surface that begins the process of focusing light. The lens, located behind the pupil, fine-tunes this focus, ensuring that light rays converge precisely on the retina. Together, they allow us to see objects clearly at various distances. Any irregularities in these structures can lead to vision problems, highlighting their importance in healthy eyesight. Corrective lenses, such as glasses or contact lenses, are designed to compensate for the eye's focusing errors. They alter the path of incoming light so that it focuses correctly on the retina. For example, concave lenses help correct myopia, while convex lenses address hypermetropia. By choosing the right lens, people with vision defects can enjoy sharp and comfortable sight, making corrective lenses a simple yet powerful solution. Scattering of light occurs when light rays encounter small particles in their path, causing the light to change direction. This phenomenon explains why the sky appears blue during the day and reddish at sunrise and sunset. Shorter wavelengths, like blue, scatter more easily, while longer wavelengths, like red, pass through more directly. Scattering is a key concept in understanding the colors of our natural world. Human eye is remarkably adaptable to different lighting conditions. In bright environments, the pupil contracts to limit the amount of light entering the eye. In dim light, the pupil expands to allow more light in. This adjustment is controlled by the iris and helps protect the retina while ensuring optimal vision. The eye's ability to adapt quickly is essential for activities like moving from a sunny outdoors to a dimly lit room. Myopia, or nearsightedness, is a common vision defect where distant objects appear blurry while close objects are seen clearly. This occurs when the eyeball is too long or the cornea is too curved, causing light to focus in front of the retina. Myopia can be corrected with concave lenses, which diverge light rays so they focus properly on the retina. Early detection and correction are important for maintaining good vision. Hypermetropia, or farsightedness, is the opposite of myopia. Here, close objects appear blurry while distant objects are clear. This happens when the eyeball is too short or the lens is not curved enough, causing light to focus behind the retina. Hypermetropia is corrected with convex lenses, which converge light rays to focus them on the retina. Proper correction ensures comfortable reading and close-up work. The eye perceives colors thanks to specialized cells in the retina called cones. There are 3 types of cones, each sensitive to red, green, or blue light. When light enters the eye, these cones respond to different wavelengths, allowing us to see a wide range of colors. The brain combines signals from the cones to create the full spectrum of hues we experience every day. Retina contains 2 main types of photoreceptor cells, rods and cones. Rods are highly sensitive to light and enable us to see in low-light conditions, but they do not detect color. Cones, on the other hand, are responsible for color vision and function best in bright light. The balance between rods and cones allows us to see both in darkness and in vivid color during the day. Once the retina converts light into electrical signals, these signals travel along the optic nerve to the brain. The brain's visual cortex processes this information, allowing us to recognize shapes, colors, and movement. This complex process happens in fractions of a second, enabling us to react quickly to our surroundings. The brain's role is vital in transforming raw data from the eyes into meaningful images. Every human eye has a blind spot, a small area on the retina where the optic nerve exits the eye. This spot lacks photoreceptor cells, so no image is detected there. Normally, we don't notice the blind spot because our brains fill in the missing information using data from the other eye. The blind spot is a fascinating example of how the brain compensates for physical limitations in our vision. Optical instruments like microscopes and telescopes use lenses and mirrors to magnify distant or tiny objects. Microscopes allow us to see details invisible to the naked eye, while telescopes bring distant stars and planets into view. Both rely on the principles of refraction and reflection, showcasing the power of optics in expanding our understanding of the universe. Color blindness is a condition where a person has difficulty distinguishing certain colors, usually due to a deficiency in one or more types of cones in the retina. The most common form is red-green color blindness. While it doesn't affect overall vision, it can make tasks like reading colored charts or choosing ripe fruit more challenging. Understanding color blindness helps us appreciate the diversity of human vision. Polarized sunglasses are designed to reduce glare from surfaces like water, roads, and glass. They contain a special filter that blocks horizontally polarized light, which is the main cause of glare. By allowing only vertically polarized light to pass through, these sunglasses enhance visual comfort and clarity, making outdoor activities safer and more enjoyable. Light is essential for vision. It travels in straight lines and can be reflected, refracted, or scattered depending on the medium it encounters. The journey of light from its source to our eyes involves many interactions, each contributing to the rich visual experiences we enjoy. Understanding light's behavior is key to unlocking the mysteries of vision and color. Refraction is the bending of light as it passes from one medium to another with a different density. This principle is fundamental in optics, explaining how lenses focus light and how prisms create rainbows. Refraction is responsible for many everyday phenomena, from the apparent bending of a straw in water to the focusing power of our eyes. Dispersion refers to the separation of light into its component colors due to different degrees of refraction. This is why a prism can create a spectrum from white light. Dispersion is not only a beautiful phenomenon, but also a crucial concept in understanding how we perceive the colorful world around us. Scattering is the process by which small particles in the atmosphere deflect light in different directions. It explains why the sky is blue and sunsets are red. The degree of scattering depends on the wavelength of light and the size of the particles. This concept is vital for understanding many natural optical effects. Accommodation is the eye's ability to adjust its lens to focus on objects at different distances. The ciliary muscles change the shape of the lens, allowing us to see both near and far objects clearly. This process is automatic and essential for everyday activities like reading and driving. Photoreceptors are specialized cells in the retina that detect light. There are 2 main types: rods, which are sensitive to low light, and cones, which detect color. Photoreceptors convert light into electrical signals, forming the foundation of our visual experience. Optical instruments use lenses and mirrors to manipulate light, enhancing our ability to observe the world. From magnifying glasses to advanced telescopes, these tools rely on the principles of refraction and reflection. They have revolutionized science, medicine, and our understanding of the universe. Polarization is the orientation of light waves in a particular direction. Polarized sunglasses use this principle to block glare by filtering out horizontally polarized light. Polarization is also used in photography and scientific instruments to enhance image clarity and contrast. We've explored the wonders of the human eye and the colorful world it reveals. From the intricate structure of the eye to the fascinating phenomena of light, color, and vision, each concept deepens our appreciation for the science behind sight. Understanding how our eyes work, the causes of vision defects, and the principles of optics empowers us to care for our vision and marvel at the beauty of the world. Let's continue to observe, question, and discover the secrets of vision.